Problem 67 reads, two positive point charges are located on the y-axis at y equals s over 2 and negative s over 2. Find an expression for the potential along the x-axis. So, just to draw out this problem, just so we have an idea of what we're looking at, here's our axes, our x and our y, and we have two positive point charges. One at positive s over 2 and one at negative s over 2. So that gives us a total of distance of s. But we're trying to find the potential, not the potential energy, but the potential over on the anywhere on the x-axis. So we'll draw out our little triangle here and we'll call these distances r. So if we just look at our basic equations for potential, we know first off that potential energy, U, so delta U, let's make that a little darker, delta U equals E times the charge times the distance. But as we know, distance is just the distance from the charges, so it's just R in this case. But we want potential, not potential energy. So in order to get potential, we do potential energy over this Q equals ED, or voltage equals ED, which is VED, which is what we talked about in class the other day. So this is the equation we'll be ultimately using, but in order to break it down a little bit more, VED equals the electric field, which we know from past is KQ over r squared. But in this case, because the electric field is no longer a vector, because it's in voltages now, it's not in the point charge like we did in the past, we don't need that little r hat there. And then times r. And then one of these r's will cancel, giving us KQ over r equals voltage, or potential. So, using this equation, we'll need a superposition problem, which just means that both of these charges are acting on this point right there. So we'll need the first one, which is KQ over R, and this will be point 1 and this is point 2, but because that they're both charged Q, we don't really need to distinguish which each one, because they're both an R distance away from the point we're looking at, and they're both the same charge. So then it'll just be KQR plus KQR. And in this case, we can simplify this to 2KQ over R. But we don't want just a generic R. We can make this different R because we know the sides. We know that this is S over this dimension right here is S over 2, and that this dimension over here is S over 2. And then we also know that the point is X distance away from the points. So since we know the vertical dimension and the horizontal dimension, we can just split R into components, or Pythagorean theorem, which just means R equals the square root of S over 2 squared plus X squared, giving us the ultimate answer of 2KQ over square root S squared over 4 plus X squared. And that's your answer. Pretty simple. Just have to break it down. The hardest part is realizing that this is going to be a superposition problem and that you're going to have to add these two equations up.